Kristen,
Hello, Professor Griffin. How are you?
doing okay.
Oh, okay. Oh, I'm tired.
Uh,
I had to work out for a little while. Trying, gotta lose all the quarantine weight I gained.
uh, I understand. I'm
Yeah.
trying to make this. Yeah, there we go.
Oh.
How come there's a stuff over here that I want to get rid of? I don't know how to do that. I don't know if you can read that. It looks blurry to me. Can you read that stuff?
It's a little blurry.
Yeah, it is.
I mean, I can read part of it.
What if I got closer? Maybe I need to be closer. I can't get much closer. Wonder, wonder if I can. Wonder if I could get it closer. I don't know. Maybe that's a little better. Why is there some goofy thing over here that I don't want? I tried to draw the circuit over there, the cycle, but it's blurry on mine. It's blurry on yours too?
Yeah, it's a little blurry.
Dang.
I have a question on
Yeah,
your
go
little
ahead.
thing there. How come Q would be negative? Because if we had already found W and it was negative, and you do delta U equals Q minus W and delta U is 0, wouldn't the Q have to be a positive 1154?
Okay,
That?
let me, you might be right. You could get a thank you point for this.
I mean, I don't know. I mean,
I wish I could read that. I can read it on here. It's clear as a bell on my board. But what you're talking about is this 1154.
Yes.
And it's a process from 1 to 2. Now, see, from
Yes.
1 to 2, you have a heat transfer per mass leaving. From 3 to 4, you have a heat transfer per mass entering. You actually have 4 of these heat transfers per mass. There's one coming in here, a little Q from 2 to 3. There's one going out here, a little Q from 4 to 1. There's 4 of them. But now what you're asking about is delta U from 1 to 2.
Mm-hmm.
Is Q from 1 to 2 minus little w from 1 to 2. Now,
Right.
delta U should be 0 because from 1 to 2, that's an isotherm.
Right.
The internal energy doesn't change any. And you can read that okay, what I did there. You can read that.
Yeah. Oh, it's because since it's negative and that's already a negative, it makes it a positive, like in that equation.
Well, let's see if it works. Now the work is negative because it's compression. Right. So the work is a negative 1154. So that means the Q's got to be negative.
Okay, I just wasn't thinking about it like that. I was just, I forgot that. I don't know. Never mind. Thank you.
The algebra did okay on that. Now let's answer some of their questions. Let's see. We still have 5 minutes.
Yeah.
Let me see who's with us. I'm going to check here. Participants. Oh, we have Levi and Tyler. We've got a good crowd. Yeah. They're checking in. But let's get the what do they call that? I forget the name of it. That ETA thing. That's the my mind just went blank. Help me. Very good. Excellent. Efficiency. Let's get the efficiency. Well, on this particular problem, if you'll read it, I think they said there is no regenerator. What that means is you got to pay for both of these heat transfers. It's going to cost you money. So we're going to get the net work here. Let me do that. Net work on this cycle is, I don't like it being blurry like that, but we're getting more and more customers here. Tyler, Levi, Kerman, Jackson, got a good crowd. But the network, that's what I'm trying to cook up right now, the network per mass. And here it goes. It's 4466 minus 1154. I'm getting 3312 kilojoules per kilogram. And of course, you'll get the same answer here for the net heat transfer per mass. But if you want the efficiency, you have to take the net work and you have to divide by what costs you money. Now, what costs you money are both of these. You got to put both of these in here. 2773, 4466. See that 2773, that's this heat transfer here. You got to pay for that. And this 4466, that's the heat transfer here from 3 to 4. You got to pay for that. Costs you money. And so what you get for your efficiency on this cycle is 2773 plus 4466. Wonder if I did that right. I'm getting 0.4575 is the efficiency for our cycle. Now,
and where did you get the 3312 from?
I added up all of the works.
Oh, the nets. Never mind.
Yeah.
Okay, I knew that.
The
okay.
sum of all the works, they call that the net work. Well, per mass. But thanks for asking. That's a good question.
Yeah.
Now I want to show you guys, this one didn't have a regenerator, but if it did, I want to show you what will happen. They'll take this Q41, which is 2773 going out, and they'll put it through this regenerator thing. They'll put it in this regenerator, and they'll send it back in here, Q23. See, Q23 is 2773 going in. And that way you don't have to pay for that, see? I'm sorry, what? Somebody said something. Okay, so if you have a regenerator, you don't have to pay for that 2773. You get rid of it. And here's what you'll get. You'll get an efficiency with the regenerator equal to this, which is 3312 divided by 4466. It's much higher. It's 7416. 74%. The Stirling engine has a very large theoretical efficiency. In fact, you can't get any higher than that because that's equal to the Carnot efficiency. Let me calculate the Carnot efficiency. Hey, look, there's a little bit of room right in here. If people just tuned in, we're going over problem 1082. It's a Stirling cycle. how do you spell Stirling? S-T-E-R-L-I-N, Stirling cycle. And these are the numbers. And I ask you to finish it. I think I left some blanks there. Man, I wish you could read that, but it's kind of fuzzy, Kristen says. But let's see, what was I? I was going to tell you about the Carnot efficiency. Now we studied Carnot cycles. And the Carnot efficiency, there's a formula for it. It goes like this. I don't know if you remember that. It was a while ago. But now the catch is those temperatures have to be in Kelvin. Okay, well, let's plug it in and see what happens. 1 minus, well, it'd be 310 over 1200. Okay, put that in your calculator. Let's see what you get for if this was a Carnot cycle. 1 minus 310 divided by 1200. Boy, Jove, I'm getting 0.7416. The same efficiency that we got if you had a regenerator. That makes the Stirling cycle the cycle with the highest theoretical efficiency, which is good. It's sort of like shoot for the moon and you might hit the barn. No engine's going to give you this 0.7416, but at least it's not forbidden. It's in the realm of possibility if you had a very expensive low friction Stirling engine with a regenerator, because the Carnot, remember, is a reversible. There's no friction, there's no irreversibilities. It gives you the highest possible efficiency. And so does the Stirling, theoretically, with the regenerator. So we did that. Now, what if I ask you for the mean effective pressure? Let's do that. I'll come over here and I'll refresh your memory. The mean effective pressure, you don't add these pressures up and take the average. That's not what it is. What it is the, it's the net work. You take the net work and you divide by your delta V. Well, you see, you got your V's. Where are they? Right here. Yeah. Delta V. What that would be V1 minus V2. That's your delta V. Okay. And we have our net work. I got some room over here. Let me write it over here. Your mean effective pressure on this Stirling cycle is 3312 kilojoules per kilogram divided by 6.437 minus 1.0732 cubic meters per kilogram. And what you'll wind up with is kilopascals. Well, let me do that. Here goes. Well, I got a mean effective pressure of 617 kilopascals. That doesn't make sense. I must have done something wrong. Because look at these pressures, 100, 600, 232, 387. There's no way. There's no way. I must have done something wrong. Let me do it again.
That's not 232, it's 2,323.
Oh,
So, and I
oh.
got the 617 also.
I did as well.
Yeah, yeah. You honking thank you point for Kristen. It's 2,323. There we go. Okay, now let me do it right. Okay, now I got lost here. Oh, well, what about that though? That's right. And that's right. Oh, yeah. Yeah, I understand now. Yeah. This is the main effective pressure. And see, the pressure really goes up to 2000 and something, but it's only there for just an instant. You understand that? At state 3, that's when you have your highest pressure and your highest temperature, but it's only there for just a tiny, tiny moment. And so this is reasonable. It makes sense. Thank you, Kristen. It makes sense now. Okay, well, we did that. Now, the way we got some of these was with, I was going to show you how you could check that. I don't want to bore you too much, but for instance, we're going to do one check here and show you that it'll work. I need a little room here. And then I want to talk about what I want to talk about. We're going to find this, we're just kind of checking our work here. We're going to find the work from 1 to 2, the work per mass. That's a little w. We're going to go from a 1 to 2. The work should be negative because it's compression. And we got a lovely formula that works like this. And that it's polytropic n equals 1 is what it is, because it's an isotherm. It's an n equal 1. See, PV to the 1 is P1 V1 to the 1 is equal to P2 V2 to the 1, which is equal to RT, where T is a constant from 1 to 2. So it's polytropic with an n equal 1. Now I'm going to plug this in. We're going to see if we get the answer. We're checking our work. Okay. Well, I got a little room here. P1 is 100 kilopascal. V1 is 6.437 cubic meters per kilogram. And then we're going to go natural log of V2, which is 1.0732 divided by 6.437. Okay, I'm going to put this in my calculator, and if we're very, very lucky, it should be minus 1154 if we did this right. Let's try it. Can you guys read that? It's fuzzy on mine. All right, here goes. I'm plugging all this stuff in. One 1.0732 divided by 6.437 natural log times 100 times 6.437 equals. I'm getting negative 1153. Well, I don't know. I got negative 1154 here. I think we're okay. I must have rounded something off, but I'm pretty happy with that. Let's don't fight over it. I guess we rounded something off someplace. but we checked our work. We got 1153. That's 1154. I'm pretty happy with it. Okay. Did you have any other questions about our Stirling cycle? Well, okay. What we're going to do now is we're going to do a Carnot cycle. I talked to you about Carnots. I'm going to erase all this. I hope you understood all that.
Yes, sir.
We're going to get rid of it, and we're going to talk about a Carnot cycle now. We did one of these a long time ago. I hear some kids. No, that's fine. Okay, now on your final, which we'll put on Blackboard Sunday afternoon, I hope. There's going to be a cycle. Now, here's the cycles we've studied. We've studied Carnot, which we're going to do here in just a minute. In fact, it will be problem, let me see if I can find it here. I picked out a problem. It's actually in chapter 5. Yeah. It's this one's 5-104E. And see, we need to know how to work in English, senor. Absolutely. But here's the cycles we've studied. Carnot, Rankine, refrigeration, Otto, diesel, and Stirling. I wish we had time for more, but we don't. But how many is it? Well, that's 6 different cycles. And you know you're going to have one, and you're going to have to make the property table and fill in all the little boxes. And what we're going to do right now, because it's been a while, is we're going to do this Carnot cycle. But you know one of these is going to be on your final. Okay, we are going to do problem 5-104E. You should have all of these in your notes that we worked on in the past. Now remember what a Carnot cycle is. It's 2 isotherms, 2 isotherms, and 2 adiabats. That's what it is. And it's reversible. It's reversible. Okay, well, let's look at ours here. And now we're dealing with air. Let's draw the cycle here. We've got 2 isotherms, so those are in red. So we'll put those in red. Here we go. Do they tell us the temperatures of those? Let me read it. It says here, yeah, 1200 Rankine and 600 Rankine. This one's 1200 Rankine. This one's 600 Rankine. We're working in English. We've got to know how to work in English. And we're doing a PV diagram. And it tells us here, if you read the problem, it says figure 521. I wonder what that is. Let me go back and look just out of curiosity what they're talking about here. 521. See what they're talking about. Anybody know what page it's on? Figure 521. Yeah, I'm in the wrong chapter. Just a minute, not chapter 5. And I'm looking for 521. There it is, Carnot cycle. Yeah, there it is. Okay. I found it. It happens to be on page 160 if you're interested. But what they did was they go 1 to 2 on the isotherm, and they go 2 to 3 on an adiabat, and then they go from 3 to 4 on an isotherm, and then they go 4 back up to 1. You've got 2 adiabats. These are adiabats. Remember, adiabats are steeper than isotherms. You can see they're steeper. Here's your isotherms. Here's your adiabats. Now let's make our table, and we'll have a fun time filling that in. Hey, I kicked that and things look better. Let me kick it. There we go. Sometimes you just have to kick things and they work better. Okay, here we go. Process 1 to 2, 2 to 3, 3 to 4, 4 to 1. We're going to plot up the P, V, T, delta U, Q, and W. We're going to plot all that stuff up. And you're going to have to do this on one of your cycles on your final exam. But it's really easy. Okay, here goes. Reading the problem now. We are doing 5104E for Inglés, senor. We're dealing with air. And it says 1200, 600. We did that. The heat added at the high temperature is 100 BTUs per pound mass. They're talking about this right here. That's your little Q12 is 100. You know where that goes? It goes right here. 100 BTUs per pound mass. Keep reading. And the lowest pressure in the cycle is 10 psi. Well, you know where that is? That's at state 3. 10 psi is at state 3 psi. There we go. We got that. Find the specific volume pressure for all 4 states. Blah, blah, blah. We're going to use CV and CP. And you guys remember what those are. CP for air is 1004. Wait a minute. Wait a minute. That's metric. We can't use metric. We're in Inglés, senor. That's 0.24 BTUs per pound mass Rankine. CV is 0.171 BTUs. Maybe we should look that up to make sure. I don't want to lie to you. Go to the back where they have
It's correct.
Inglés. We already checked it. Not that I don't trust you, but I'm just going to look for sure, make sure that's right. Air, by Jove, I got it right. That's right. And R is 5334 foot-pounds Oh, gee. Foot-pounds. Force per pound mass Rankine. You might look that up too. Let me double check that. Go to the back there, snoop around. And for air, it says, it's got to be in English. Am I in English? Yeah. Air. I don't see it. Air, 5334 foot-pounds force per pound mass Rankine. Yeah. Okay, I got all that stuff right. Good. Hey, let's put in this state one is 1200 Rankine, shall we? Here we go. State two is 1200 Rankine. See, these are all in Rankine. State 3 and 4 are 600 Rankine. Hey, look at here. P3V3 equals RT3. Look at here. I don't know if you can see this, but P3V3 is equal to RT3. We should be able to get V3. I'm going to give you guys a minute and a half, 2 minutes. I want you to solve for V3. Hey, you could have to figure that out on your final for sure. We have to know how to use the ideal gas law in English. So go ahead. Go ahead and find this V3. If you know P3 and T3, find V3. I'll be quiet. Go.
So I'm just verifying on R, is that 53.34 or 5334?
No, it's 53.34 foot-pounds force per pound mass Rankine.
Thank you, sir.
Yeah, it's
I
in
know
the
I could have
back.
looked it up. I was just being lazy for a second.
Oh, no, that's okay. Good for you. Was that Dawn?
Yes, sir.
That was Dawn. I recognize your voice, Dawn. Well, I got an answer. I don't know if I gave you guys enough time, but I got 2.222. We could put a 3 there, maybe. Anybody getting that?
I got 22.23.
Oh, I got 2.22. Maybe I need to do it again. Let me do it again. You're right, and I'm wrong. What was that, Dawn, that just spoke up?
No, sir.
It was
Give
Kerman.
Dawn- Well, that was Kerman. Kerman. Honkin' thank you point. You're absolutely right. It's 22.23. Good going, Kerman. Okay, well, let's get some more boxes filled in. Let's see. I think we got all the info here. Yeah. Okay. Hey, wait a minute. I just thought of something. Two of these Q's should be zero. Which of these little Q's is going to be zero? See these Q's? Which ones are the adiabats?
2 to 3 and 4 to 1.
2 to 3, 4 to 1 are zeros. There we go. Good going. Now, two of these delta U's are zero because, see, isotherms, they don't change their energy any. The energy depends on the temperature, and if it stays the same, there's no delta U. So which one of these delta U's are the isotherms?
1 to 2 and 3 to 4.
1 to 2, 3 to 4. Hey, looky here. Our first law, this is a control mass. It's a piston cylinder. You know the first law, it goes delta U equals Q minus W. If you know delta U and Q, you should be able to get W. Going from 1 to 2, the W is either going to be plus or minus 100. Which is it? Plus 100 or minus 100?
Plus.
It's plus. Can you see going from 1 to 2 is expansion? So the work is plus. And see, that obeys this. You got 0 equals 100 minus 100. It worked. Yay. Good deal. Okay, now what? Well, hey, we could get these delta U's here. Let's do this. There's some room right here. Let's do this delta U from 2 to 3. You know what that is? That's going to be CV delta T from 2 to 3. Well, CV is 0.171, 0.171 BTUs per pound mass Rankine. But what's the change in temperature from 2 to 3? And looks to me like negative 600. What do you think?
Yes,
You
sir.
got colder. You got colder. Look, you went from 2 to 3. You got colder. And so now we can get delta U. Here goes. I'm going to do it. I'm getting a negative 102.6. Double check me now, but I'm thinking this is a negative 102.6. Y'all, little Southern talk, y'all getting that?
Yes, sir.
Great. Hey, looky here, back to the first law. Back to the first law, delta U equals Q minus W. If you know delta U and you know Q, you should be able to get W. Going from 2 to 3, you know what? I think it's 102.6. But is it plus or minus? Plus or minus?
It shares the same.
Is
So
it-
like with negative 102.6 for Q, it would be negative 102.6 for W.
Well,
Oh,
no,
wait.
it's
2 to
positive.
3. Sorry.
It's
I was thinking 3 to 4.
oh, okay.
I apologize.
You're forgiven. But it has to be plus because look, going from 2 to 3 is expansion, and expansion work is always positive. And if you plug this in here, let's plug it in and see if the numbers work. Delta U is minus 102.6. Q from 2 to 3 is 0. And then you go minus a positive 102. Hey, that worked, guys. The algebra works. See there? We're doing great. Okay. Well, now let's do, what's next here? How about this one? from 4 to 1, you're getting warmer by 600 degrees. Wouldn't it be the same numbers? Wouldn't it be a plus 102.6? We could write it out if you want. But going from 600 to 1200, you're going up 600. And so on this equation here, it would be a plus 600 times 0.171. You get 102.6. You can write it out if you want. Anybody want me to write that out?
Yes, sir.
You're okay? All
Yes, sir.
right. All right, now looky here. We've got 102.6, a 0. We should be able to get this work per mass. We should, if you know two things in your first law. The work here should be, it's either plus or minus 102.6, but which is it? Going from 4 to 1.
Minus.
It's minus. It's minus. Okay. Hey, we made a lot of progress here. Let's see what this stuff is here. What is that, 3 to 4? You know, there's a couple of ways we could do that. One way is the work from 3 to 4 is equal to P3 V3 natural log of V4 over V3. Now, do we know P3 and V3? Yeah. Yeah, we do. Do we know V4? Uh-oh. We don't know that. And we don't know. No, it was just a thought. Can't do that one. We don't know everything. But let's try this. Delta U equals C sub B delta T. Let's try that. Delta U from, we're doing, I just had a senior moment. I think we're doing 3 to 4, aren't we? Yeah, 3 to 4. No. We're doing 4. Yeah, we want to do 3 to 4. We don't want to do that either. Well, maybe you guys have a better idea. We got some empty boxes here, guys. And you have any ideas? Boy, I hear a lot of silence there. Let me look at who's playing
We
here.
use the integral of PDV for little work. Kind of like yesterday or 2 days ago, whenever it was.
Well, to do that, you'd have to know what the function is for P. And the function of P, you got 4 different P's here. And I don't think we have a function for P. I mean, theoretically, what you just said is true. But here, let me show you how to do this. I need a little room to work here. I'm going to have to make some room. But we're doing 5104E if you tuned in late. It's a Carnot cycle. We did one years ago. This is problem 5104E. It's in English units. It's a Carnot cycle. And here's my plan. We have an equation that goes like this. Going from T2 to T3 is equal to, it's air, right? I think we can use that because from 2 to 3 is an adiabat. And this equation works for adiabats. And do we know T3 and T2? Yeah. Hey, look at here. We know T3 and T2. Do we know P3? Hey, look at here. Do we know K for air? You can look it up. Look, we could get P2 from this equation, couldn't we? Yes, we could, Mr. Griffin. Okay, well, let's do it. Here goes. We're going to use that equation. We're going to get the P2. T3 is how much? 1,200. No, 600. T2 is how much? 1,200. Doesn't that give you a half? I think it does. It gives you 600 over 1,200. T3 is 600. T2 is 1,200. 600 over, yeah, it's a half. A half. It's equal to P3, which is 10, divided by P2. 1.4 minus 1 all over 1.4. Okay, now I'm going to shut up for about a minute and a half or 2 minutes here. Can you read my writing there? I hope so. 1/2 is equal to 10 over P2. 1.4 minus 1 over 1.4. All right. Find P2. I'll be quiet and let you find P2. Go for it. Well, I got a P2. Did you get 113.1? Now, if anybody wants me to write
That's
that
what it
out,
was.
that's what you got?
Yeah.
Good. If anybody wants me to write that out in detail, just speak up, and I will.
Yes, sir. I want.
You want me to write it out? Okay, let's
Yes,
do it.
sir.
Here goes. I'm going to write it out. And I just need this room here. We'll sacrifice a little room here. Okay, we got 0.5 equals 10 over P2. When you put all that in your calculator, here's what I get. I get 0.2857 if you just put that in your calculator. And then what I did was well, there's several ways to do this. One way is you can go natural log of 0.5 is equal to the natural log of this thing, which is equal to 0.2857 times the natural log of 10 over P2. That's one way to do it. Step by step, we're doing it. Now I'm going to take the natural log of 0.5, and I'm getting negative 0.6931 something equals 0.2857 natural log of 10 over P2. Now I'm going to divide by that. Let me do that. 0.2857. And step by step, this is what I have now. 2.4261 equals the natural log of 10 over P2. Now what I'm going to do is take the anti-log. I'm going to hit that little e to the x button. Here goes, e to the x. And I'm getting 0.088378 something equals 10 over P2. And I know you can take it from there. I know you can take it from there. Let me do it and see if I get the same answer. I'm getting P2 is 113.15 or something like that. Coy, did you follow that?
Yes, sir. Thank you.
You are very welcome. Okay, hey, look at here now. Look, P2V2 equals RT2. We're going to do that now. Here goes. We'll make some room here. We're going to go P2V2 equals RT2. Now we got P2. We got R's over here, remember? We got T2, it's sitting right here. I'm going to take another minute of your time, and I want you to solve for V2, and I'll write this out carefully if anybody wants me to. But go ahead, I'll shut up for a minute. Get that for me. Well, I got a V2. I've got 3.93. Now those units are cubic feet per pound mass. That's what those units are. The units on this P are PSI. The units on all of these are BTUs per pound mass. But I'll be glad to write this 3.93 out in detail if anybody wants me to.
Will you please? Because
Oh,
for some
I'd
reason
love
I'm
to.
not getting my V's the same.
Yeah, I keep
Good.
getting mine wrong too.
And even on the other one, and I don't know what I'm doing wrong.
Thank you so much. Let's do it. Here goes. The dirty little secret is you got to multiply over here by 144. And students, forget that. Inches squared per square feet times your V2. And see, V2 is going to be in cubic feet per pound mass. So that'll cancel with the square feet and just give you a foot per pound mass. But it'll get rid of the inches, won't it? Wait a minute. Never mind. Now R is 5334 foot-pounds force per pound mass Rankine, and T2 is 1200 Rankine. Now the Rankines go bye-bye, and what you have is foot-pounds per pound mass. Now what this is cubic feet per pound mass. Oh, I'm forgetting my P2. Just a minute. Let me scoot that in there. I'm forgetting. No wonder it didn't work. P2 is 113.1. 113.1 pound force per square inch. There you go. You see how that's PSI, pounds force per square inch. The square inches go bye-bye, but you got to have that stinking 144 in there. Oops, well, I forgot my V now. Let me scoot this over just a little bit. Okay, Kristen, 144, 113.1 times V, 5334, 1200. You plug that into your calculator and you will get 3.93. Try it.
I'm trying now. 1 second.
Take your time.
I did it. Yay me.
Yay, that's more like
Thank
it.
you. Thank you.
Anytime, just ask. Now, we still have some empty boxes here. We got to fill those in somehow. See, we don't know what P4 is, and we don't know what V4 is. We don't know what P1 or V1 is either. Kind of got a problem there. But we don't give up easy around here. I need a little room, and we're going to see if we can't find those missing boxes there. Remember, going from 1 to 2, the work per mass on that isotherm is P1V1, natural log of V2 over V1. Now let's circle the stuff we know. Oh, see, we got problems here. We don't know P1 or V1. But you know what? P1 and V1 is equal to RT1, isn't it? P1, V1 is equal to RT1. Now we do know R and we do know T1, don't we? And we do know V2, don't we? And we do know the work from 1 to 2. Yeah, Hey, look, we have an equation here with only one unknown. See it? So here, let me put in the numbers. This is 100 BTUs per pound mass. R is 5334. Foot-pounds, force, pound mass Rankine. Temperature is 1200 Rankine. Then you have the natural log of V2, which we know, we figured it out, it's 3.93. Kristen got it, over V1, which we don't know. Look here, only one unknown, but now there's a catch. The units. We're going to have to do something about the units. Guys, here's a rule. Whatever the units are on the right-hand side of an equation has to be the same units on the left-hand side of the equation, and they aren't. But we can get it that way. See, a BTU, I need this room here. We'll just sacrifice a little bit here. A BTU is 773 foot-pounds force per BTU. I'm going to show you that in the book here. let me dig that out of the book for you. If you shop around in your book, you will see you will see energy. Someplace they have energy. Where the heck is it? Power, length, energy. Here we go. A B. This is wrong. It's 778. There's 778. Here, let's be nitpicky about it. This is in Appendix A. It's 778.17. It's Appendix A. Go to your book. I bet you've seen that before, but it's back there. It's in Appendix A, and a BTU is equal to 778.17 foot-pounds force. Now you see that way you get rid of the BTUs, and you have foot-pounds per pound mass on the left, and on the right, you get rid of your Rankins, and you have foot-pounds per pound mass on the right. Hey, we got foot-pounds per pound mass on both sides of the equation, and we can solve it now. Here, let me put a big circle around it here so you don't get too confused. We are going to solve this equation now for V1. Now, this is a little bit hard, but it really doesn't scare us. We can do that. I'm going to shut up. You got a minute and a half. I want you to find V1 for me. Go for it. I feel so secure and safe. Nobody would possibly sneak up and try to scare me. I don't need to worry. I don't need to worry about anybody sneaking up and scaring me. La 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 la. Gabriel, are you sneaking up and trying to scare me? Gabriel, are you? Hey, I got the answer, guys. I did this and I got V1 is 1.165. 1.165. Did anybody get that?
Yeah, that's what I got.
Yay, that's two of us. Good going. I bet you guys can do that. This is a little bit tricky with the English, but I'm sorry. Life is hard sometimes. Hey, we're making, oh, that scared me. Oh, that scared me. He's going to give me a heart attack. And then these students won't have a teacher. And that's not funny. He's laughing. Okay. Hey, looky here, guys. P1V1 equals RT1. if I only had some room, how about over here? Look at all this room I got over here. Look here, P1, V1 equals RT1. Now this time, Kristen, don't forget to put the 144 in there. You got to put a 144 in there in order for the thing to work. All right. I'll give you guys another minute. I want to see if you can get P1. See, we're missing P1. We've got V1. We know R is still sitting right here, and we know T1. All right, go for it. Here goes. After giving you that lecture about don't forget the 144, I forgot the 144. And I got a ridiculous answer. But then I put the 144 in there like you're supposed to, and I got 381.5. How about you guys? 381.5. Man, we're making progress here. I need an aha.
Yeah, I got that too.
Yay, there's two of us. Good. Kristen, did you get that?
I'm working on it, sir.
Take your time. Take your time. Take your time while we figure out how on earth we're going to do this. There's some missing boxes down here.
Well, can't you get the W from 3 to 4 by using the W equals PV?
Hey, I like it.
LNV, yeah,
I
that one.
like it. Here, she's got a good idea. Here, let me write that. In other words, we're going to do the same thing from 3 to 4 that we did from 1 to 2. Let me make the room here. I don't see why that wouldn't work.
And yes, I did get the 381.5.
Yay, good going. Okay, now we're talking about little w from 3 to 4. That's equal to P3V3, natural log of V4 over V3. But you could write P3V3 as RT3, couldn't you? Oh, yes, I could. See, we could write that as RT3, and we know T3, and we know V3. Look at here. We know V3, we know T3, we know R, and auga. Auga. Kristen had a great idea, but we don't know the work from 3 to 4. Let me show you how to get that. If we only had that, I think we could get this V4 thing. And here's the dirty little secret for doing that. I need some room here. And besides, this is good review for your final. Do you remember these? I call them schematics. I call them cycle schematics. I call these the cycle schematic. And see, what you have here is the high temperature, which is 1200 Rankine. And down here you have the low temperature, which is 600 Rankine. And here you have the net work. Let's use little letters. You got a little w here, network. You have little qh here and little ql here. And we have these lovely equations. We have what they call the Carnot efficiency, or the maximum efficiency. It's based on temperatures. And what it's equal to is TH minus TL over TH. And we know all of those. Is 1200 minus 600 over 1200. You know what? The efficiency of this Carnot engine is 0.5. I'll write those numbers out if anybody wants me to. But we know what they are. But then we also have the actual efficiency. We've done these before. And what that is the network divided by the Q sub H. See, you have to pay for that Q. This is 1, 2, 3, 4. You have to pay for that Q1 too. It's 100. So the net work, if this is 100, the net work has to be 50 to give you a 0.5. See, these are equal. The maximum possible is equal to the actual in a Carnot engine because it's a reversible engine. And so when you add these up, this has to be a minus 50. So the net work will be a 50. And this has to be a minus 50. And so the net heat transfer per mass is a 50. Now, I don't know if that made any sense, but that's how you get it. You have to go back and you have to look at this schematic here and see, we know what this is. This is 100. This is 50. It's going down. So you could write minus 50 if you want, but it's going out. So it's really a minus 50. And this is 50. 50 and 50 make 100. Did that make any sense at all? I'm hoping. Okay, now back to Christian's idea. The work from 3 to 4 is minus 50. But see, that's BTUs per pound mass, isn't it? This English stuff is really kind of nasty. To get foot-pounds force, you have to multiply that by 778. Foot-pounds per BTU. That'll get rid of your BTUs, and you'll have foot-pounds per pound mass. And over here, what you'll have, I just need the room. I don't have enough room. Over here, what you'll have is 5334 foot-pounds per pound mass Rankine times 3 to 4 is 600 Rankine, isn't it? Times 600 Rankine. Natural log of V4 over V3, which we know. V3 is 22.23. A little bit nasty, but here's our equation. A little tiny bit nasty. you'll discover that this term will be negative because V4 is smaller than 22.3. And this term over here will be negative because you get a minus 50 there. And if you plug in the numbers, we can get V4. Here goes. We're going to plug them in and get them. Here goes. Again, I'm going to shut up and I'm going to see if you can plug in these numbers in this equation and get V4. If you can't, I'll do it step by step with you if you want me to. Okay, here goes. I'm doing it. Well, I've got my V4. I got 6.59 cubic feet per pound mass. Anybody getting that?
Yes.
There's one. Anybody need me to write out the numbers in more detail? Okay. Well, now we're going to get this pressure at state 4. Here we go. Remember, I need some room here. Let me make some room. Remember, you have to go P4V4 equals RT4. But to get the units to work, you got to multiply by 144 over here on the left. All right. And we know V4 now. And we know T4. We should be able to get this. Okay, plug it in and see what you get. Well, I got 33.72 for the pressure, 33.72 PSI for the pressure. Anybody else getting 33.72 when they plugged in all those numbers?
Yeah, I got that too.
Yes, sir.
Or it's over here, yeah. Well, okay, good. So how many boxes are there? About 24? this would be worth 25 points. Basically, each box is worth a point. Let's go over this one last time about the efficiency. There's an actual efficiency, and there's a reversible efficiency, or you could say it's maximum. Now, this is given by this formula that we know and love for Carnot cycles. You could write it like this, or you could write it like this. It's the same thing. It's just an algebra trick. Can you get from here to here? I bet you can. And if you plug this in, this is 600 and 1200. That's a half. So you know what this is? It's a half. Now, if you do the actual, what you do is you take this net work right here, which is 50 BTUs per pound mass, and you divide by the 100. That costs you money. The 100. So you got to burn some gas or diesel or something, coal. I don't know. You got to have some kind of heat source, and that's probably going to cost you money unless you use a geothermal maybe or solar. You could use solar. That would be pretty cheap. But see, that gives you 0.5 also. Yeah, this gives you 0.5. Because this is a Carnot cycle. The actual and the maximum are equal because it's a Carnot cycle. Now, the way it really works for a real engine is the actual is going to be less than the maximum on a real engine. Like your diesel engine or your auto engine or your Rankine cycle. The actual will be less than the maximum. But on the Carnot, see, it's a reversible cycle. Well, we've gone over that Carnot. We did one year, not years ago, but a while ago, maybe January or February. And we just did another one. Do you have any questions on any little old thing? Well, okay, I'm going to post a final Sunday afternoon, and you guys can have a fun time doing that. Do good on it. And I'm working up your homework grades. I might get those posted tonight at the rate I'm going. It's possible. Yeah, I'm working on them.
For all 4 classes, you might have them
Yeah.
posted tonight. Okay.
Yeah, I hate to promise you, but there's a probability that I'll have them done. Yeah, we'll
Okay.
try.
Mr. Griffin, I have a question.
Sure.
You haven't post our second test key on Blackboard.
I haven't.
No,
Your
you
second test
haven't.
isn't posted on Blackboard? Well,
Uh,
I will. I
the
will
key.
post it.
It's the key.
Oh,
I'm
the
asking.
key. The
Yes.
key. Let me write that down. Second, this is your Thermo class. Second,
It's also for strength and material.
I didn't post that either.
No, it's the key
I didn't.
to test. I mean, yeah.
You know
Test
what?
2
I
key.
could do that, Coy, and that would be good for you guys to study.
Yes,
I
thank
could
you.
do that. I could post the keys to Thermo and strength the second test.
Yes,
Thank you.
sir.
Thank you for asking that.
Thank you.
Thank you. I'm still listening.
Well, just like since this is like our last class period for all classes, I know I asked you about a couple of them, but I can't remember which ones I've asked if I'm missing anything in. I mean, you don't have to look right now. I know there's like other people on here. Even if you could like email me if there's anything you're missing in any of the 4 classes for me. I just don't want to.
Well, you're not missing anything in this class.
Okay. And I know I asked you, like I said, I know I've asked you on some of them, but I can't remember which ones were which. So, okay. I guess I'll just wait until I see when you post the homework. So will it be posted like, is it just going to be a total homework point?
Yeah.
Or
it's
are they going to be in, so I won't know based off that if I'm missing anything?
No, it'll be a percentage.
Okay. Okay,
And,
well,
and I curve it a little bit. So
okay.
if you figure out your percentage, mine will be higher than yours because I curve it a little bit.
Oh, goody.
Yeah.
I like curves. Curves
Yeah.
are good.
Yeah, they are.
And that's the same for all of them?
That's
all
the same for
classes?
all of them.
Perfect. Okay, well, I know, like I said, hopefully I'm not missing anything in the other ones. If you, whenever you're doing the homework points, if you happen to see something that I am missing, do you mind emailing me?
Let me think about it.
Okay, all right,
Okay.
because I shouldn't be. I mean, I do all the
Yeah.
assignments, but I don't know. Okay, all right, well, thank you.
Thank you.
Bye.
Bye-bye.
Thanks, sir.
Thank you. Adios, muchachos.
Bye.
Bye.
Bye-bye.
Thank you.
Bye, Eli.
Thank you.